This video will cover normal distributions, continuous distributions, density functions, cumulative distribution functions, and the 68, 95, 99.7 rule. The single most important distribution in statistics is the normal distribution. It's a continuous distribution, and it's the basis of the familiar symmetric bell-shaped curve. The mean of the normal distribution is in the center. The standard deviations are marked at equal distances from the mean. Any particular normal distribution is specified by its mean and standard deviation. By changing the mean, the normal curve shifts to the left, or right. By changing how spread out the standard deviations are, the curve also changes. Standard deviations can be spread out wider or closer together. Therefore, there are really many normal distributions, not just a single one. The normal distribution is a two-parameter family, where the two parameters are the mean and standard deviation. Here's a tool you can play with online that illustrates a normal distribution. In real life, it looks like a triangular-shaped pegboard into which balls are dropped. When there's an equal probability that the balls will drop either left or right, their final placement forms a normal distribution. However, when the probability of the balls dropping left or right is unequal, which is something you can experiment with using this tool, the distribution changes. The formulas for mean and standard deviation are very complex, but you will not have to compute them because the software will. With continuous variables, there is a continuum of possible values, such as all values between 0 and 100 or all values greater than 0. Instead of assigning probabilities to each individual value in the continuum, the total probability of 1 is spread over the continuum. Thus, the shaded area within the bell curve will always have an area of 1. The key to this spreading is called a density function, which acts like a histogram. The higher the value of the density function, the more likely this region of the continuum is. A density function, usually denoted by fx, specifies the probability distribution of a continuous random variable x. The higher fx is, the more likely x is. Probabilities are found from a density function as areas under the curve. So for example, the shaded portion under this bell curve represents the probability of x being between 65 and 75. The cumulative distribution function, or CDF, is the probability that the variable takes a value less than or equal to x. It's the total area under the normal curve up to x. The beauty of the normal curve is that no matter what its mean and standard deviation are, the area between the mean minus 1 standard deviation and the mean plus 1 standard deviation is always about 68%. The area between the mean minus 2 standard deviations and the mean plus 2 standard deviations is always about 95%. The area between the mean minus 3 standard deviations and the mean plus 3 standard deviations is always about 99.7%. That means almost all values fall within 3 standard deviations on either side of the mean. That's true for all normal curves, no matter their shape. But how good is this rule for real data? Let's go ahead and check out an example. Here's our data. The mean of the weight of 120 women runners in a sample is 127.8 pounds. The standard deviation is 15.5. Here's what our distribution would look like. Let's look a little more closely at that distribution. 68% of our 120 runners is about 83 runners. According to the 68, 95, 99.7 rule, those runners should all fall within 1 standard deviation of the mean weight of 127.8 pounds. That is, 83 of our runners should fall between 112.3 and 143.3 pounds. When we check our data, we see that 79 runners fall within 1 standard deviation of the mean. Furthermore, 95% of our group, or about 114 runners, should fall within 2 standard deviations of the mean, or between 96.8 and 158.8 pounds. The data shows that 115 runners fall within 2 standard deviations of the mean. Finally, according to the rule, 99.7% of our runners, or 119.6 runners, should fall within 3 standard deviations of the mean, or within a range of 81.3 pounds to 174.3 pounds. According to our data, all 120 runners fall within this range, so it seems as if the rule is pretty accurate in this case. This concludes our video on